So today let's first finish this theorem. I copied what we have from last class. So we talk about let's review first. The third part is that the alpha, the phi of as you proceed by that the phi xk plus 1 is phi of xk as you do this, right, with the initial guess with initial guess x0, we need to show that this goes to alpha, right? It goes to alpha. It converts to alpha, right? For any initial guess x0. Okay, for this particular theorem. The proof is simple but very cute, right? So I just want to show you that. So essentially, we need to look at this, right? We need to look at this. The difference, the error. If you want to show xk goes to alpha, xk goes to infinity, you keep applying, which again we're going to maybe do some coding later, for you to see numerically, like practically, that it converts to exact solution, maybe 4, right? And so you show this distance goes to 0, right? It's getting closer and closer and closer. The trick is that I can rewrite this as two phis. We'll invoke that theorem we talked about many times already, and you'll see the power of that theorem that we quickly can see. All right. So that's my contribution. If I want to write xk minus alpha as phi of something minus phi of something else, can you tell? Xk is easy, right? You know, that's from the iteration. So that's x. I try to write more clearly. Xk is phi of xk minus 1. That's for sure, because that's how the scheme works, what I just wrote down. Xk plus 1 is phi of xk for any k, right? So what about alpha? Alpha is equal to phi of what? Anybody? Alpha is a solution of the problem that we were trying to solve. Then we turn that equation into a fixed point, which means phi of alpha equals what? Alpha, which means alpha equals phi of alpha, the other way around. So that's the trick. I can replace alpha by phi of alpha because alpha is the fixed point. You plug in alpha into phi, it doesn't move. That simple trick brings us to some symmetry. You see, they're both phi of something. That's symmetry, right? Before one is x, one is alpha. That's ugly. Now they're both phi of something. So we can what? We can apply this thing again, the picture that we talked about many times. And I really hope you understand that, right? That's a very nice geometric understanding of this, and I hope you remember. And that's true for multi-dimension as well. And it's a very useful thing, as you see need now. We're going to apply this to conclude a powerful theorem. This is equal to phi prime, right, at some c, which is between the two inputs, times the both absolute value, so xk minus 1 minus alpha, right? So it's a slope. If you divide both sides by xk minus 1 minus alpha, you get a slope is equal to the derivative at some middle point. Not a middle point, some point in the middle. Okay? Is everybody okay with that? We're just applying that theorem we talked about many times. Let's make sure, okay? All right, so I take that everybody understands that, all right? And of course, we should put absolute value sign here because we start from the absolute value sign. And we know, what do we know about derivative? The assumption is that the derivative is less than k. I don't know c, but I do know the phi prime c is less than k. Right? So, as you know, going back to a question when we talk about the theorem, sometimes we don't care about c. Because look here, we only care about phi prime. If we know something about phi prime, we don't really care about the c. Less than c times x k minus 1 minus alpha. Right? Look what we, if I'm copying what we are start from, xk minus alpha as absolute value. We have this. Absolute value of xk minus alpha is less than k times absolute value of xk minus 1 minus alpha. If I go through what we did above, that's true for any k. This is less than. This is less than. I keep that k. If I turn the second part into xk minus 2 minus alpha, what do I get? What should I keep? What should I put in the middle? Another k, right? Because you apply the same procedure again, each time you get a k outside, and the index decreases by 1. I basically do what we did above and replace that k by k minus 1. You get the same inequality for k minus 1. Xk minus 1 minus alpha is less than k times xk minus 2 minus alpha. So which is k squared, right? And if you keep going, I ended up at x0 minus alpha, because k minus 2 turned into k minus 3, k minus 4, all the way to k minus k. You get that capital K, the number smaller than 1, to what power? Can you figure that out? That's right. K to the capital K to the little k. Right. The trick is you look at the two numbers, right? When it's k minus 1, you get 1. When it's k minus 2, you get 2. So the rule, the pattern. This pattern you all can figure out when you were in primary school, right? Sum is fixed. So when 0 is k. K plus 0 is k. K minus 2 plus 2 is k. All right. So the good thing now we're going to use assumption that the capital K that's a bound for the derivative is less than 1. Less than 1, right? Less than 1. So if you keep raising a number that's less than 1 to some power little k, remember the little k is a step size. We keep applying the scheme. The little k goes to 2, 3, 4, 5, 100, 1,000, however large you want, right? So a number smaller than 1 raised to a large number would go to what? Do you have that concept from calculus? Go to 0. Go to 0. Even if the capital K is 0.99, you keep raising the power, you're going to get 0. As long as it's less than 1. Right? If you don't believe it, you have to do it by hand or on computer by yourself. So, which means we showed that the absolute value of the difference go to 0, which means xk goes to alpha as k goes to infinity. Of course, we're not going to go to infinity in real life. We stop somewhere when they're close enough, right? Which we'll talk about the stopping criteria soon. Questions? So that's what gives the name the contraction, right? The contraction. So the difference, the distance is contracting to 0, right? The xk is contracting to alpha. The prime, the phi prime, sort of like is coercing, provides a force for the contraction, right? It's a contraction property of the fixed point iteration. And you now know from the theory, you now know the key quantity you should observe is phi prime. Look at phi prime, right? Phi prime. That's a clue. Okay. And you want from that. So again, the key quantity to observe is that phi prime. The phi prime, right? Do you want to be large or small? Small. I want it to be small. The smaller phi prime is, the faster it converges, because you're taking that guy to the case power. Remember, look at the proof. That's why we talk about this proof. Otherwise, you don't know. I can tell you the result. Just look at this, and smaller the better. But you don't understand why smaller the better, right? Why? Here is why. That's why. What the last line of proof is why. Because if your capital K is 0.1 versus 0.9, it's certainly very different. You take 0.1 to the cubed, you get 3 digits. You take 0.9 to the cubed. What's that? You don't even get 1 digit, right? 0.9 cubed. That's the difference, right? So the smaller K is, the faster the scheme converges. All right. We're going to do hopefully later today to do a little experiment on computer, but I will also give you homework, right? And here is a clue for that. Look at phi prime. That's quantity to look at. To add to that, I'm going to give you just list a second theorem. This time without proof. It's basically the same vein, but slightly more general. So if phi is again, we always want the C1s continuously differentiable, right? This time in the neighborhood omega alpha of alpha. The last theorem requires, we know something about the whole domain, right? We talk about the whole domain, the derivative is less than k. That's a very strong assumption. If your problem does satisfy that, good for you. But that's not the case all the time. So we try to make the assumption weaker, which is the result is more general, right? Does that make sense? Right? Yeah. So if you can, instead of the whole domain, again, we're trying to provide a theorem that has a weaker assumption. If you assume something that's weaker, your result is more general. That's the logic here, right? And we, instead of look at the derivative on the whole domain, we just look at the derivative as the solution, right? As solution. Of course, most of the time you don't know the solution, so this is still quite ideal, right? So you can find a neighborhood. You don't need the whole domain. If you find a small neighborhood can be small, as we will talk about Taylor series. Talk about neighborhood, MBHD, right? We use that. Then there exists a delta, all right? A delta larger than 0, such that the sequence of iterate, the sequence of our iterate xk will converge to alpha given we have x0 minus alpha is less than delta. In a more easier to understand language, right? What it will mean in this case is that as long as the initial guess is close enough, all right, let me try to explain this. In fact, let me write that down, right, because it's so important. And so the implication of this, right, the implication is that if your fixed point iteration diverges, say e.g. your Newton's method, again, that's most likely what you're going to use at someday. Then most likely, of course, you might have some other bug. So you typed something wrong. If the less trivial bug, the most likely you need to adjust your initial guess so that it is close enough to alpha. All right, to alpha. Again, that will probably a more practical use of this. Does that make sense? Any other questions? Yeah. So maybe later today we'll apply some. Maybe we can write that down here. I think my favorite example is something like. I mean, you can certainly cook up similar examples: x minus x to the fifth, and another one is x plus x to the fifth. All right, and it's quite interesting in the sense that certainly they both have alpha equals 0. Those are simple. If you plug in 0, you get 0. So 0 is fixed point, right? There is fixed point. And if you look at phi I prime at alpha, right? Phi I prime at alpha. I is 1 or 2. I'm not writing both. I'm just writing one together. So you're going to take the derivative. Again, the key quantity is to look at is the derivative is 1 and is plus minus or minus plus for minus for 1 plus for 2, 1. 5, 0 to the fourth power. So that's of course just 1, right? Just 1. It doesn't satisfy the condition. This is a borderline. It's right at 1, not less than 1, right? And these two would be very different if you still apply the fixed point. And we'll probably just do a third one, which is if we need to solve, if we try to solve this guy, right? X cubed plus 4x squared minus 10 right? With it is written as f, it means we need to solve for this equal to 0. So we can turn this into a fixed point. Maybe like you can define your phi. Again, we need to f of x equal to 0 turn into phi of x equal to x, right? We talk about it. Solving 0 turns into a fixed point. So if you add x to both sides, you are going to get one phi, maybe phi 3 is x cubed plus 4x squared minus 10 plus x. We did a little example for solving for any f equal to 0. If you add x to both sides, you get a fixed point, right? F plus x, f equal to 0, f plus x would equal to x. So I just add x to my f. That could make one phi. Another choice is that if you look at that f, and I can do something different. Let's say I can have x squared times x plus 4, right, is equal to 10. Right, equals to 10. I factor out the x squared, which means my x squared is 10 over x plus 4, which means that my x, if I'm assuming I'm looking for a positive root, I'm trying to look for a positive root, then my x is equal to square root of 10 over x plus 4. All right? This little derivation shows that we can take phi of 4 equal to what? It should be in this form, right? Phi of x equal to x. So phi of 4 is simply square root of 10 over x plus 4. Right? That's for phi of x, because we ended up with x equal to phi equal something, x equal some other function. Okay? So what do coding for this later? Questions? And certainly you can try this yourself, right? Or any other zero problem. You're looking for zero of a nonlinear equation. You can try to change it. There are multiple ways to make that a fixed point. Right? I do want to talk about the applications of these two theorems above. To let's say the chord and Newton's. Right. Number one, for the chord, remember the chord is that xk plus 1 is xk, right, minus f of xk divided by something, right? We take that something to be the slope of the line connecting the two endpoints, right? So that's b minus a over fb minus fa times fxk, right? fxk. So which means our phi of x, the phi of x equal to x, the phi of x is that guy on the right hand side, right? Turns that into a function of x. So this is x minus b minus a over fb minus fa of f of x. Right, that's the guy on the right hand side. So if the iteration converges, you get x is equal to phi of x. And again, we're just repeating what we concluded. We need to look at the phi prime. So let's actually look at the phi prime. So the phi prime, you take the derivative of this guy, right? Is 1 minus, for the coordinate something is constant. So you just let me b minus a over fb minus fa times f prime of x, right? F prime of x. So if we were to apply the first theorem, the one with a strong assumption, which of course will get a strong conclusion, so we don't need to worry about the initial guess. You put initial guess anywhere, you will converge, right? If you want the phi derivative is less than 1, or maybe for the second one, if you want the this guy is less than 1, right? The different neighborhood, this guy is less than 1. So which means the less than 1 means that the phi prime alpha is less than 1 and larger than negative 1. Right? Okay. Which has an assumption on your f. Right? Maybe I should read one more step instead of jumping. So this is 1, negative 1 is less than that guy, 1 minus b minus a over fb minus fa times f prime x, f prime alpha. This is less than 1. So what does that imply for f prime alpha, or that whole thing? B minus a over fb minus fa f prime alpha, right? I can subtract 1 from all sides. So you're going to get a 0, less than 0, you change the sign. That's larger than 0, and less than 2, right? Less than 2. You see that, right? In particular, this is not a crazy assumption if you think about it. What is, if that alpha happens to be that Kasi in the picture, right? The unknown Kasi in the picture. What is b minus a over fb minus fa times f prime at that Kasi? What is it? It's 1, right? It's 1 because that f prime Kasi is equal to the slope, and as b minus a is the reciprocal of that slope. So you multiply that, you get 1. 1 is certainly between 0 and 2. All right? For the second one, the Newton, which do a little bit of derivation, you'll see why Newton is fast. Based on what we concluded from the theorem and based on what we're going to derive here, hopefully you have a tangible understanding of why Newton is fast. And then you do some coding yourself, that's even better, right? So again, the Newton is xk plus 1 is equal to xk. They all have the same form. Again, we derive 3 of them together, right? That divided by something, we take that something to be f prime at xk. Right, xk. So, which means our fixed point iteration function, phi, that black box, is x. You turn all the xk to x, right? X minus f of x divided by f prime of x. They all have xk in it, so they all become x, right? Not like the one above, we don't have nice. The one above is very easy to take derivative. So what does this mean? The phi prime x, again, according to look at its phi prime. The phi prime x is 1. We always get a 1 because it's xk. Minus the derivative of that thing, right? That we need to use the quotient rule exactly. So we're going to get f prime x squared, right? The derivative of the top, which is f prime x, times the bottom, which is f prime x, minus the top times the bottom derivative, f double prime x. All right, double prime x. So if you simplify this and write as a common denominator, you'll see this is just f prime x squared. On top is f of x times f double prime x. Double prime x. All right, double prime x. Okay, double prime x. All right. So we know that if f prime alpha is not equal to 0, then, and we already know, right? We know f of alpha is equal to 0. We know that because alpha is a solution to that. Then the phi prime of alpha is equal to what? What is phi prime alpha? Plugging alpha, what do you get? 0, right? Yes, 0. You plug in alpha, you get phi f of alpha on top. Remember, we concluded the derivative of phi is the capital K, the small, because k to the little k's power, the smaller it is, the faster. Now it is 0. Right? It is 0. Of course, it's just 0 at that one point. It's not going to be 0 in the neighborhood. But at least, very likely, it is very small because at that point, 0, right? It's a continuous function. So in a small neighborhood, the derivative is really small. And that k is a bound. The k will be small, so it converges fast. That's the intuition. And you're going to show the convergence order, right? I think maybe I put it in the homework already. I forgot. And the question is, what if the f prime alpha is equal to 0? Then we have a 0 divided by 0 situation, right? Because on top is f of alpha is 0, on bottom is f prime alpha is equal to 0. Okay. In that case, I'm going to provide maybe a couple of homework to lead you to the conclusion. But to add as that background, right? We have so there's definition for the background of that homework. Again, I will maybe write up 2 problems to do it step by step. If f of alpha is equal to f prime alpha, which is first derivative, right? If we were to write, and this is equal to f n minus 1's derivative at alpha, they're all equal to 0. But f m alpha is not 0. It's not 0. Then we say that alpha is a root or like a 0 of f of x with the so-called multiplicity m. It's multiplicity m. For example, right? For example, if you want to solve x plus 2 equal to 0, certainly the root is minus 2x minus 2. And f, if you plug in minus 2 equal to 0, this derivative is 1, it's not 0 anymore. So the multiplicity is 1, right? It's 1. M is 1. You only get, if you keep taking your derivative, you only get 1, 0. Right? F prime, and when m is 1, it's already not 0. So m is 1. the negative 2 has multiplicity 1, right? Say if you have x squared times x minus 2 is equal to 0, then we all know it has two solutions. In 0, the solutions is 0 and 2, right? 0 and 2. And they're different in the sense that 0 has a different multiplicity, because if you take the derivative, and plug in 0, you still get 0. So 0 has multiplicity 2. So the multiplicity, this guy is 2, that guy is 1. Okay? So relating with what we're doing, right? So again, a homework which I will type up is that let's see, is if alpha is a 0 of f of x of multiplicity m, then phi prime alpha is equal to 1 minus 1 over m. Right? And in that case, the phi is a phi for the newtons, all right? Because, what in that case we need to, in that case what we just did is not enough. Basically, you need a little more tool from calculus. Multiplicity is a starting point. What we did, just take the derivative and use the quotient rule. It's not enough to calculate the phi prime, because it's 0 divided by 0, which is not 1, all right? Can be infinity, can be 0 in principle. So you need to dig deeper. That's a motivation here. Again, the phi is equal to that x minus f of x divided by f prime x, all right? In that case, we should use the modified Newton's method. Newton's method, all right? Which is the case that xk plus 1 minus is equal to xk minus m times fxk divided by f prime xk. So if m, for the case we talked about above, right? For the case we already resolved, we concluded phi prime alpha is equal to 0. For this case, f prime is not 0, which means our m f prime is not 0, meaning our m is 1. So its derivative is 1 minus 1, which is 0. So it's consistent with what we did, right? So 1 minus 1. When m is 2, like in this case, is 1/2. So this phi prime is getting larger and larger. So your original Newton is getting less and less effective. You see the point? And in this case, the trick is you can modify it. And of course, it's not very, very useful because, if you don't know the solution, you don't really know its multiplicity. But for polynomials, in case sometimes you do know some information, then it's useful, right? So you see the link, right, between what we did already. All this is trying to resolve what we couldn't do, what we couldn't. Let's see, here. We ended up with 0 by 0. It's f alpha is 0, f prime alpha is 0. So you're dividing 0 by 0. What do? A lot of tools from calculus. And this is one of them. What I'm laying out for you. And again, I'm going to type that up. But that will be the second homework, second set. All right. So the last thing today is I want to mention the stopping criteria. Stopping criteria. So we're applying the methods, right? Iterative method scheme. When do we stop? When do we stop? You need to set that up like in your code, a while loop. When your assumption is satisfied, you stop. That's a stopping criteria. Okay. So for the two families of schemes we talk about, if you solve f of x, and I will just provide a understanding, and we talk about criteria and then talk about what is the advantage and disadvantage of that criteria, right? In particular, we're going to talk about something like conditioning. It's an important concept. So this is like maybe the first time we ever mentioned conditioning, right? So we did mention when we started talk about the solving for the zeros. We mentioned, well, one criteria we can use is that because it should be some quantity you can compute, otherwise you cannot really monitor, right? So you can, every time you have a iterate, I have xk, I plug in that into my f, because I need to solve for the solution f alpha, which is f of alpha is 0. So this guy should be small, right? Here, this is small. This is less than epsilon. Epsilon is small number. So whatever you want, maybe you want 6 digits, then set epsilon to be 10 to the negative 6. It depends on your application, right? A small number. That's something we can observe, because we can compute. Where you are given f, you have your current iterate. So that's computable, right? Computable. Here, mathematically, I want you to have an understanding, at least a visual. I'm going to plot a picture for you, a visual understanding of, that's something we can observe. That's not your end goal. Remember, the end goal, what we really need is that xk minus alpha, right? You're solving for the exact solution. What you really need is this guy go to 0. This guy is small. This guy is small. But you don't know alpha, so you cannot really observe that, right? So you cannot use that as a stopping criteria. You understand? And so ideally, you should observe that, but you couldn't. You take one step back, right? It's compromise, right? So always what do we do in life? You have to compromise. Something you cannot compute, compromise, and observe something that's related, but good enough, right? But with that, you should be, keep in mind what are you compromising, right? What are the consequences? So that's what I want to talk about here. So the question is that f of xk always a good indicator, a quantity that you observe, right? And I want to show you, like, maybe just in 1D. All right. at two extreme cases. All right, one is that I'm going to have a f which is very steep at the alpha. Right, can even make it steeper. The other is that I have a alpha. I have a f that's very flat. All right. So you see, if I'm in fact making the same mistake, that's my xk, right? Same distance away, xk, and that is my alpha. So my xk and alpha are the same. Xk minus alpha are the same, all right? And if you look at that height is at fxk, right? Over here is this guy. This guy is our fxk, right? Does that make sense? So for a very different function with 1D version, basically it's a case that derivative is large versus small, right? And for if I don't know the function, so I only look at the f of my xk. In this case, my f of xk is tiny. I take a look at this, I say, oh, that's tiny. That's my stopping criteria, so I'm going to I think my solution is, my current iterate is close enough. Over there is large, I'm going to continue, but in fact they have the same accuracy, right? So here, you think you can stop, but in fact, that's still quite a bit of error, or that's what I'm trying to say, right? So if you think you can stop here, you're being as optimistic or pessimistic. As last time I was talking about this, we got some confusion, right? You're being too optimistic, right? Because you think you can stop, in fact, it's what you perceive is better than what's in real life, right? So that estimator, that indicator would in this case would be optimistic. In that case, it would be pessimistic, right? The same indicator. Of course, we cannot really do too much about it for this particular setting, but you should have that in mind. That's conditioning. What you observe is small. So the conditioning, the concept is that what you observed, the quantity you observe is small, doesn't really mean the solution is small. That doesn't mean the error is small, the true error that you observe. All right. And for the case of the fixed point, all right. For the case of fixed point, the criteria. The criteria here is that you look at, because the same thing can be applied to the f of x as well. Just a second type of criteria is that you look at this guy. A second criteria, again, this can be used for the f of x as well. If you look at the distance of the two successive iterates, right? Iterates, and if this is small enough, this is small, which means you're not making too much update to a current guess, right? Which is probably a good sign that it converges. Converge means it gets close to the exact solution. the closest, when in the final steps is so close, it's not moving much. That's intuition, right? Intuition. We're not going to talk more details of this. Instead, let's maybe look at do a little bit of coding here.